Imagine entering inside a CPU where millions of operations happen every single second.
Today we are not learning the theory. We are going to visualize how the CPU performance improved using the exam-based animations.
I am Ria Trisha. My ID number is 24C126.
I am Ishan Sastry. My ID number is 24C115,
We are the students of Charotar University of Science and Technology.
and we are in the second year of Computer Engineering department. And today we are going to acknowledge you all about our topic.
Visual analysis of CPU performance improvement techniques. Let's step into the processor and explore how modern systems achieve high speed.
Yeah. So before we go to our topic, I will generalize our topic. How the CPU improve performance can be improved. CPU performance improve techniques includes the six different techniques or theory concept behind it. For out of them, I am going to explain you first topic, which is called pipelining. So, pipelining. Pipelining is one of the fundamental technique in the CPU. It allows the multiple instructions to be processed simultaneously by dividing executions into the stages. By as a phase, the code executes memory and write back. A working principle of the pipelining is goes toward when a new instruction enters into the pipeline, the previous instructions move to the next stage instead of waiting for the one instruction completely. Entire the CPU overlaps multiple instructions just like an assembly line in the factory. This improves the throughput, meaning more instructions are completed per unit time. However, pipelining introduces the challenges such as data hazards and control hazards, which must be carefully managed and maintained if their efficiency. Now we are move towards our visual 3D model, which explain us pipeline in detailed manner. Now we are entering to our 3D model. Our 3D model describes the five stages of the pipelining. First stage is fetch, second stage is decode, third stage is execute, fourth stage is memory, and fifth stage is write back. In first step, the CPU fetch the informations from the fetches new instructions, then it decode it, it execute using the ALU, and it's the output of the ALU in a data cache, and then write back it. Now, the second topic of scalar multi super processing will be explained by my friend Riyakesh.
Okay, so the next process is
Okay.
So the next topic. Okay, so now next topic is superscalar execution. Superscalar architecture takes performance a step further by executing multiple instructions in parallel within a single clock cycle. Instead of processing one instruction per cycle, the CPU uses multiple instruction units like ALU and floating point units. This allows independent instruction to learn simultaneously, increasing instruction level parallelism. However, the process must analyze dependence between instructions to avoid conflict and ensure correct execution. Now, the practical implementations are like we modify plus we can browse and
Execute the multiple instructions as soon as their required data is available rather than strictly following the program order or following the program order. If the instruction is delayed, for example, waiting for the memory, the CPU continues the executing other independent instruction. This reduces the time and improve overall efficiency. Structure called reordered buffer ensures that the results are committed in the correct order and maintaining the program correctness. Now let's go for the practical implementation in which we are opening a file while downloading something and downloading a large file, opening calculator instantly. So CPU keeps the slow tasks, which are minimal tasks, and focus. CPU has the large focus on the heavy tasks, so that they can provide the high performance and high calculations to that task which needs more data to be run and to be instructed. Now we will understand more briefly and more deeply by visualizing its working flow in the 3D. Where the out of order is. Similarly, it's working like a pipelining, as is a part of pipelining. So the first three functions will be the same instruction code that I earlier explained in the pipelining, and uh, the bifurcation between them, then reordering and then the issue in the queue. So reordering is for those programs which really needed more data to be register or be processed. And a issue queue is a reservation station where the operands are read which input and operands are ready and executed unit freely. Instructions do not wait in any order. Any instruction whose input are really immediately woken up in dispatch enabling the out of the execution. Now, similar process of reloading. After that reloading, we will go to the ALU, where which performs the various multiplication, addition tasks, and goes to the common bus data. After this ALU execution, it goes to the common bus data and all the reservation stations simultaneously. Any instruction waiting for the result immediately woken up and becomes eligible to execute, considering the two dynamic scheduling. And now, after this rescheduling, reordering of the tasks, CPU at the end commits the task and continue his execution as a normal. Now, third part will be explained by my friend Ria, which is a branch prediction.
Okay, so the next part is the branch prediction. Branch prediction is used to handle decision-making instructions such as if-else statements. Instead of waiting for the condition to be evaluated, the CPU predicts the most likely path and continue execution. If the prediction is correct, performance is improved significantly. If incorrect, the CPU must discard the wrong instruction, a process known as pipeline flush. Modern processes use advanced prediction algorithms to achieve high accuracy. Now, the practical implementations are like this. Give us auto suggestion and smart loading for apps. Example, like typing in search bar. Suggestions appear instantly. The CPU predicts the next action. We can conclude that it helps us in fast interactions. Now, let us see the 3D modeling of this particular topic. As you all can see, the instruction is going on and it decides whether to, which path it should be taking for a particular instruction. It must decide which instruction to fetch next before it knows the outcome, which predicts guessing which path to take specialization. So now the next topic will be explained by Shan Shastri.
So next performance improvement topic is cache memory. Cache memory. So what is the cache memory? We are generally, when we are visiting the various websites, we are asked to store our data in the cache. So cache memory is a small high-speed memory located close to the CPU. And it stores the frequently accessed data to reduce the access time compared to the main memory. The cache memory cache hierarchy typically includes the three steps L1, L2, and L3, each with increasing the size and latency. By keeping the important data nearby, the cache memory significantly reduces the memory access delay and improve overall performance of the system. Efficient cache management is the highly essential for the high-end computing. For example, practical implementation of cache memory is give us opening recently used applications easily, quickly, as we have opened the website in our previous task. So its data is already stored in our cache memory. So our CPU will do not have to make effort to fetch the data from the main memory. It will store in the cache memory. So data will be transferred and fetched easily to the main memory. So now we will we see the study model how cache hierarchy works. So here is the cache hierarchy. It's a thode, mostly there is the three level of cache hierarchy that I already mentioned you: L1, L2, L3. Okay. So the first is CPU core. It loads the instruction and requests the data for the specific memory addresses. Here it is connected to the memory address where the cache, and then it will directly connect to the L1 cache, where faster and smallest cache will drive to the CPU core, and typically it stores the 32 to 3064 KB data and 4 cycle latency. Highly temporal and spatial locality means most exactly accesses hits here. Then second is L2 cache. It's slower than the L1, but typically its storage capacity is very high, and it's directly connected to the L1. Then third is L3. It's sad with as today in today's scenario, we are using those computers which have multi cores. So the L3 cache is connected to all the cores of the CPU, and it typically stores the data capacity ranges from the 8 to 64 MBs, and it has a latency of 40 cycles per minute. So when L3 misses any data, it must be fetched from the off-chip DRAM and cross the code the data, sharing the massive coherence happen at this level. To solve these misses, we have a DRAM fetch penalty section where the data which is not fetched, it will stored here, and it will return to the L1 directly. Now the sixth part will be explained by my friend Ria.
Okay, so the next topic is multi-core processing. Modern CPUs contain multiple cores, allowing them to execute multiple tasks simultaneously. Each core operates independently, enabling true parallel processing. This is especially useful for multitasking and applications like video editing, gaming, and data analysis. Cores often share resources such as shared memory, which improves communication and efficiency between them. Now, the practical implementations are like multi-core core handles multiple tasks. We can video edit plus browse plus background apps do all at the same time on a quad-core CPU. Example, we have 4 cores. One is doing video rendering, second is doing browsing, third is doing OS, and fourth is doing background apps. We can include that. It helps us in true parallel processing. Now let's see the 3D implementation of the process. Okay, so as you can see, there are basically multiple cores, which are like 8 in this scenario, and they all are doing multiple tasks. As you can see, the instructions are coming and they are all performed at the same time. So basically it helps in true parallel processing, and it's very important part of the computer. Okay, so the next part will be explained by my friend Ishan Shastri.
Yeah.
Tar mummy ne kaam se.
The second and last topic is the single CIMD, which means single instruction and multiple data. It allows the single instruction to be processed in the multiple data element at once. This technique is widely used in the applications such as graphics processing, scientific computing, and machine learning. So instead of executing the same operation multiple times, SIMD performs it simultaneously on the multiple data points. This dramatically improves the performance for data parallel tasks. The practical implementation of this particular topic is widely used in the video editing and graphics processing. Let's observe and let's learn more in depth using 3D model visualization. Yeah, you can see the 3D in this SIMD model. There is a load array which transfers the data and which is processed by the multiple CPUs and cores, which provides a single instruction which processed by multiple CPUs, and then it will stored into the vector, which vector generally used for the highly processing thing, which it acts like an accelerator
to process any data more easily and efficiently, and at the end is stored into the main memory as a for the high performing output. In this way, I can conclude the SMMD is the one of the best topic for the machine learning and video editing and graphics, 3D graphics modeling. Now we are moved
Yes,
towards the last portion of our record. The topic is conclusion.
thus we can conclude that these techniques, pipelining, superscalar execution, out-of-order processing, branch prediction, caching, multi-core architecture, and SIMD collectively enable modern CPUs to achieve extraordinary performances.
Yeah, understanding this topic is essentially for the appreciating the how the computer operates efficiently in today's fast-paced digital world.
CPU processing is not just about speed, it's about intelligent design.
Yeah,
Thank you.
thank
We
you.
hope you like our video.
Yeah.
Have a nice day.